All right, so first I'm going to go over some of the properties for your definite integral. So first one, if you have an integral from a to a f of x dx. Oh, make that a little better. So normally it's a to b. I wrote that one as a to a. That would be like the integral from 2 to 2. And if you compare that to the beanstalk thing we just looked at, it would be like, how much did it grow from 2 hours to 2 hours? Well, if no time has gone by, then nothing. This is going to end up being 0. So if your lower boundary and your upper boundary are the same, like you haven't accumulated any area under the curve. So it's going to be 0. Right, and then the next one, integral from a to b f of x dx equals negative integral from b to a f of x dx. So if you reverse the boundaries, that's going to make your answer the opposite sign. So if it's positive, it'll be negative, negative, it'll be opposite. That should make sense. It's like you're traveling the other direction. You're accumulating area backwards. And then third one, integral from a to b f of x dx plus the integral from b to c f of x dx equals the integral from a to c f of x dx. I always explain this one like you're going on a road trip and you just did a rest stop at B. So like we went from A to B and then we went from B to C. So we went the whole distance from A to C. That's also like your transitive property. Okay, so those are our 3 integral properties. And so for this first one, we're going to use this information to answer these questions. So we're given integral from 1 to 3 of x squared dx, that's 25. Integral from 1 to 3 of just x dx, that's 7. And integral 1 to 3, and if you want to put a 1 in there to show that the integral is not empty, it's like 1 dx, that's going to be 4. But notice the boundaries are the same for all of these. They're all 1 to 3, which is important because those are the numbers we're going to be using in these problems. If they were different, then we couldn't use that information to do the problem. So letter A says integral from 3 to 1 x squared dx. So that's the x squared. We're looking at this one. And what they did is they reversed the boundaries. So instead of 1 to 3, now it's 3 to 1. So what is this answer going to be? If all we have to do is negate what it was, we reverse the boundaries. Good. Instead of 25, perfect. It'll be negative 25. Now, this one, I'm going to write as 3 separate integrals for each of the 3 separate terms so that you can see what's going on here. When you get good at these, you could like skip this step, but I want to show you what this is going to look like. So for this first part, you can take the coefficient and write it out front. So I'm going to write that as 2 integral from 1 to 3 x squared dx. So that's just this first term there, the 2x squared. And then I'm going to do the same thing with the middle term. This minus 5 will come out front. So minus 5 integral from 1 to 3 of just x dx. You can put a coefficient out front of the integral. You're basically multiplying the integral by that coefficient, but you can't take a variable out. So don't ever put like an x out front of the integral. All right, and then the last one is plus 4 integral of just dx. I'm sorry, from 1 to 3. And if you want to put a 1 in there, like so it feels like it's not empty, like I did for this one here, which is what we're going to use to answer the question. You can always put a 1 in there. It's kind of like when you have an x all by itself, it's really 1x. It's exactly like that. So now we're going to use our information to answer the question. Integral from 1 to 3 x squared dx. Well, that is 25. So this is going to be 2 times 25 minus, right? And then integral 1 to 3 of x dx, we're told that's 7. So this will be minus 5 times 7 plus, all right, and then integral from 1 to 3 of just 1 dx, we were told is 4. So this will be plus 4 times 4. So let's see what that will come out to. This will be 50 minus 35 plus 16. So what is that? 15 plus 16, so 31. But honestly, if it's free response, you can stop right here. You don't have to evaluate any further. If it's free response, you can stop. But if it's multiple choice, as you saw in your homework, you have to keep going until you can get an answer. So those arithmetic skills are still important. All right, so for that one, you are given these pieces of information. For this one, instead, you're given a graph. So we're going to have to find all of these areas first before we can go and answer the question. So let's do this first area. This first one is a triangle. Now, you're going to need to know your area formulas. Those aren't going to be given. So how do we do an area of a triangle, guys? Memories back to geometry. How do you do an area of a triangle? All right, good. Nice job, guys. 1/2 base times height. Perfect. So I'm just going to work these out off to the side. 1/2, all right, this base is 5, and the height is 4. So 1/2 times 5 times 4. Half of 4 would be 2 times 5 is 10. So that triangle is worth 10. Here we have a semicircle. If the whole circle was drawn in, it would be like that. I know it looks a little bit squished, and that's just how the graph got scaled here. But this is a semicircle. A whole circle is pi r squared. So a half a circle is 1/2 pi r squared. And so we just need to figure out what the radius is for that circle. So if the whole thing was drawn in, this would be the radius. And so that radius is 3. So again, a whole circle would be pi r squared. It's a semicircle, so half of that, 1/2 pi r squared. 3 squared is 9. So this is 9/2 pi, but it's going to be negative. Why would this be negative 9/2 pi? And kind of think about the beanstalk thing that we just did. Why is it negative? Okay, it's below sea level. It's below the x-axis. It's like an unaccumulation. Like if you think about accumulating all this area, or if you think about accumulating growth, this 10, you're accumulating, positive, and then here you're accumulating negative. Or you could think of it as like money in the bank and then money out of the bank, like you lost money. But it's below the x-axis, so negative. And then we've got this last little triangle here, 1/2 base times height. The base is 1, the height is 2, so that is going to be worth 1. And that's positive since it is above the x-axis. So now that we have all of those, and that's exactly like what was given to us here, it's just we had to find it ourselves. It's the same idea. All right, we just had to use our geometry skills and find those ourselves. So this says we want the area under the curve from -5 to 0. All right, so from -5 to 0, that's from here to here, that would be 10. Once you have these, answering the questions becomes real simple. All right, from 0 to 6, so that's from here to here, that's our -9/2 pi. And then C from 6 to 7, that's this last little triangle, so that is 1. All right, so D says we want the area from -5 to 7. So that's from here to here, that's the whole thing. So all you're going to do is add these 3 together. So 10 plus 1 would be 11, and then minus the 9/2 pi. So 11 minus 9/2 pi. You're just adding those 3 areas together. And then E is also -5 to 7. The only difference is there's an absolute value around that. What that means is you're going to treat all of these like they are positive. So you're going to add them all together and just treat them all like they're positive. So that's going to be 11 plus 9/2 pi. So if there's an absolute value, you're just treating them all as though they're positive. And then last one of these, we want the area from 0 to -5. Ooh, a little tricky. Here's 0, here's -5. We're going from here to here. That means we're going backwards. We're going this way. So what is that answer gonna be? If we go from -5 to 0, we got 10. So if we go from 0 to -5, good, we went backwards. So that is gonna be -10. Yeah, nice job, guys. Cool. We just went backwards. Now, I didn't have one on here like this, but look at the semicircle. Say we wanted the area from 6 to 0. Say we went from here to here, we were going backwards. What would that give us if we went from here to here? Yeah, good. It would be positive 9/2 pi. So you're just changing the sign. If you go backwards, it's just opposite. So these ones, now you have to draw the graph yourself and then do the area. I'm kind of like, here I gave you some of the answers. Here we had to find them ourselves. Here you're going to have to draw the graph yourself as well. All right, so let's draw a graph for this. 1/2 x plus 2. So we're going to start with our y-intercept at 2. And our slope is 1/2. So that means go up 1 over 2. And so it's going to do something like that. So that's that line. And we want the area under the curve from -2 to 4. So here's -2, and here's 4. So what shape did we get, guys? What shape is this? I'm trying to get another color. It's not a triangle because it didn't go all the way down to the x-axis. I actually have this little space here. So, so it didn't end up being a triangle. If it had gone all the way down to here, then it would be a triangle. And I know it's super tiny, I'm sorry. And I'm not perfect, so my drawing's not that great. Good, trapezoid. So this is gonna be a trapezoid. It's on its side. So this is like the right side up trapezoid. I apologize, my drawing's just not very good. All right, so we're going to do the area of the trapezoid, 1/2 height, and then add the bases together. Now the height is this distance. So if I count up those units, 1, 2, 3, 4, 5, 6 is our height, which makes sense. It's from -2 to 4, so that's 6. And then I'm going to add the bases together. This one is 1, and this one is 4. All right, so let's see. 1/2 of 6 would be 3, times 5 would be 15. But again, if it's free response, you can just stop here and be done. All right, and then this one, again, we're gonna have to draw the graph ourselves. Heads up, this one's gonna be a little fun with fractions here, which is okay. Fractions aren't the enemy. Okay, we're gonna have to be able to get through this. This is absolute value, so it's gonna be a V shape, and where it's gonna touch the x-axis is gonna be at -4/3. If you were to set this equal to 0 to find where it's gonna touch 0, it would be at -4/3. So -1 1/3. So like right there is going to be the point of the V. It's going to do something like this. And so what I would do is plug in the boundaries. We want to go from -3 to 0. So I would plug in those to see like how far we're going to go with each side of the V shape. So if we plug in -3, this will be -9 plus 4 would be -5. If you absolute value that, it will be +5. So this is the one side of the V shape. And then if you plug in 0, you're going to get 4. So this is the other side. Now, obviously, the graph keeps on going forever and ever, but we only want the area from -3 to 0. So like this graph keeps on going here. But we only want the area from -3 to 0. So we ended up with 2 triangles. And so I'm going to do the areas of each of them separately. It's 1/2 base times height. So 1/2, all right, this first one. This is 1 2/3. The way I know this is 2/3 right in here is we said that this side was 4/3. We had 1 1/3. So this is 1/3 of the way through there. So this is 1 2/3, which would be 5/3. and then times the height, which is 5. So 1/2 base times height. And then the other triangle, again, we're doing 1/2 base times height. So 1/2, the base here is 4/3. And then this height is 4. So let's see. And again, if it's free response, you can totally stop there. But let's see. I don't know how messy this is going to get. Let's see. 5 times 5 would be 25. 2 times 3 would be 6. So this is 25, 6. Plus, all right, and then this would be 16, 6. Which would be, what is that, 41, 6? All right, so we drew the graphs, and then we found the areas that we were looking for. So things you're going to need to be able to take areas of would be, trapezoids, triangles, rectangles, squares, semicircles, stuff like that. You're not going to have to take like the area of a pentagon or something. They're all like pretty straightforward. All right, and then the last thing we're going to look at today are antiderivatives, which is exactly what it sounds like, the opposite of a derivative. I want to real quick look at A, B, and C here. What are the derivatives of these? Like, for example, look at A. Everybody, what is the derivative of this function? If we were to take the derivative of this. Well, we're going to need some variables in there. I need the derivative of this. Yeah, good. So that would be 4x minus 3. Nice. All right, cool. All right, and then for B, g of x, if we do g prime, that derivative is going to be 4x minus 3. And you probably see where I'm headed with this. If we do the derivative of h prime of x, that's also going to be 4x minus 3. So they all end up with the same derivative, but they're not the same function. You can have any constant written at the end, plus 17, plus negative 100, plus 1. The derivative of any constant is going to be 0. So when you do an antiderivative, you always put plus c at the end to show that there could be a plus anything there at the end. All right. So what this looks like is you have an integral of a derivative, f prime of x dx. That's going to take you right back to the original function, f of x, but you put a plus c at the end to show that there could be a constant there. So what we're saying is the derivative of this is what's in the integral. Now this is called an indefinite integral. All the integrals we did on the other side of the paper, those are called definite integrals because they have boundaries on them. That's an area under the curve. We want the area from 2 to 7 or whatever it is. Those are definite integrals. See how all these examples we're about to do here? And if you're like, oh my gosh, that's a lot of examples, don't worry, they go really fast. They don't have boundaries on them. And that's when you need that plus c at the end. Those are called indefinite integrals. Right, so an antiderivative is the inverse of a derivative. And so what that means is you're doing everything backwards. So when we think about the power rule, what you do with the power rule is you multiply the power down and then you subtract 1 from the exponent. So we're going to do that in reverse. So when you do the power rule, you multiply the power down and then you subtract 1 from the exponent. So instead, we're going to add 1 to the power and divide by that number. So instead of multiplying and then subtracting 1, you're going to add 1 and then divide. It's those steps in the reverse order. It's kind of like socks and shoes. You know how you put on your socks and then put on your shoes, and when you go to take them off, you take off your shoes and then take off your socks. You're reversing the order of those steps. All right, but here is how these work. And I love teaching this because like it takes the first few for it to click. And then once it clicks, everybody's like, oh, I get this. These are going to go quick. The first few aren't because you're going to be like, what on earth? But then as soon as it sinks in, it's going to be like, oh, I get it. Okay. What you're looking for is a function that if you did the derivative, you would get what's there. It's kind of like Jeopardy, like this is the answer and we want the question. So I need a function whose derivative is 0. Any thoughts? Yeah, good. It's just going to be C. Any constant. Yes, 17 would be a choice, or 6, or 12, or negative a million, or 16/23. You know, any constant, if you do the derivative, you're going to get 0. All right, so for this one, you need a function. Again, it's like this is the answer, you want the question. You need to come up with a function where if you did the derivative, you would get -3 as your answer. So perfect, good. -3x plus a constant. Derivative of -3x would be -3, and then you always put a plus constant at the end, because like I explained up here, you know, you could have plus anything at the end. Derivative of a constant is going to be nothing. So you're looking for a function that would give you this as the answer for the derivative. So I need a function that has 5 as a derivative. Good, so 5x plus c. So now here I'm throwing a variable in there. So we have an x. I need a function where if I took the derivative, I would get x. So this is what you're going to do. You're going to add 1 to the power. So it's right now it's x to the first. So if I add 1, that's going to be x squared. And then you divide by whatever that is. So we're going to have to divide by 2, which means I'd put a 1/2 out front. Or you can just put the whole thing over 2. But if you did the derivative of this, you would get x. You would multiply the 2 down, they would cancel. You would subtract 1 here, and you'd have x to the first. And then for the 10, you're going to need a plus 10x, and then plus c at the end. You can always check your work by doing the derivative. If you do the derivative of this, you should get what's there. All right, so for this one, x to the third, you're going to raise the power, so x to the fourth, and then divide by 4. So you can either just put the whole thing over 4, or you can put a 1/4 out front. You see stuff like this a lot, like 1/4 x to the fourth, and 1/5 x to the fifth, and 1/6 x to the sixth, because that's how these antiderivatives work. And if you look back at the test you guys just took, look back at number 7 on the test you just took, and you'll see a lot of stuff like that in there. Because you know what I did? I wrote what I wanted your answer to come out to, and then I did the antiderivative and gave you that as the question. That's what I did. So you can go back and look at that if you want. Right here, I'm going to ignore this 1/3 for a second. Right? We're going to add 1 to the power. So this will be x to the 6th. And I need a 1/6 out front. But there's already a 1/3 there. So you'd have 1/6 times 1/3, which would be 1/18, and then plus c. So it was going to be 1/6 x to the 6th, but a 6 times a third gives you an 18th. All right, this one, I'm going to ask you guys. And the same couple of people have been answering. Let's try and get a few more voices in there. I need a function that if I did the derivative, I would get this. So like this is the answer, I want the question. You can't see? Good, nice, good job, guys. Yeah, so x to the third, if you do that derivative, you would get 3x squared plus 2x squared. If you do that derivative, you're going to get 4x, and then plus a constant. Yeah, you just had an extra 2 out front. You just don't need that 2. And again, you can always check your work by doing the derivative. If you do the derivative of this, you're going to get what's there. All right, here comes the trig. Okay, let me see if I still have my note cards handy. Hold on a second. I have these somewhere. Ah, here they are. All right, remember these? Derivative of sine is cosine. Derivative of cosine is negative sine. Remember we practiced these? We have note cards somewhere. Derivative of secant is secant tangent. Derivative of tangent is secant squared. Derivative of cotangent, these are the negative ones. All the cos are negatives. This is negative cosecant squared. And then derivative of cosecant is negative cosecant cotangent. So we're going to do those backwards, okay? So you need a function where if you did the derivative, you would get sine. And Marissa, nice job. This is going to be negative cosine of x and then plus c. The reason it's negative is because if you do derivative of cosine, that is negative sine. So we need a negative in there to cancel out because we want it to come out to be positive sine. So again, derivative of cosine is negative sine. We put that negative in there to cancel it out because we want it to be positive. Flashbacks to English class, what, just from doing note cards? All right, so here I need a function that if I did the derivative, I would get secant tangent. All right, so which one of them had this as its derivative? I'll give you a hint, it's not sine or cosine, it's one of the other four. But we need one that has this as its derivative. Good, nice job. I was waiting you guys out to see if somebody would answer. Derivative of secant is secant tangent. So this is going to be secant of x plus c. So derivative of secant is secant tangent. All right, and then for cosecant squared, we're getting close to the end of time here, so I'm going to just tell you, if you want to give it a guess, you can go ahead and type it in. All right, good. Derivative of cotangent is negative cosecant squared. So since this is a positive cosecant squared, it's the same idea as what we did there. We're just going to need to put a negative in our answer. So negative cotangent of x plus c. Again, it's because derivative of cotangent is negative cosecant squared. We just need the negative there to cancel it out. If you haven't looked at these flashcards in a long time, which you probably haven't since Unit 3, and I don't blame you, but get them back out because you're going to need them. All right, e to the x is great. It's just my favorite one. The derivative of e to the x is e to the x. So guess what? The antiderivative of e to the x is e to the x. This is 15 e to the x plus c. It's just itself. So here for the x to the fourth, that is going to be 1/5 x to the fifth minus e to the x is itself, and then plus c. Yeah, e to the x is just the best function. I just love that one. All right, this one. I need a function that if I did the derivative, I would get 1 over x. So what function has 1 over x? Good, nice, perfect. Good job, guys. All right, ln of x plus c. Oh, Joseph, I think this was you that you brought up when we did ln and you were like, well, why isn't there an absolute value? And I was like, well, I'll explain that later this year when we do antiderivatives. Today's that day.
Finally.
Value. The reason that there is an absolute value is because your ln graph looks like this. You cannot ln a negative number. So when you go back and do the antiderivative, you put an absolute value around the x. So ln absolute value x plus c. Told you I was going to explain it. All right. And then this last one, this is the same thing that we just did. Good, that made me happy too. All right, it's the same thing that we just did, except there's a 1/3 in there. And if you want to even write it like this, again, you're allowed to take coefficients and put them out front. So it's the same problem we just did, except with a 1/3 in front of it. So 1/3 ln of x plus c.